welcome everyone to today's webinar. And the topic of today's webinar is optimizing fracture healing, realistic boundary conditions. My name is Christopher Iversen, and I will be responsible for the webcast today. I'm also responsible for the sales and marketing efforts here at Anybody Technology, and today I will be assisted by my colleague Bjørn Ingelund during the Q&A session in the end. In the Anybody webcast series, we host a variety of presenters who have used the Anybody modeling system in different applications. And in today's webcast, I'm very pleased to introduce our speaker, Anne-Christine Andres from Saarland University in Germany. And Anne-Christine will present her take on visualizing the full healing process from initial post-surgery movements to rehab and daily activities using patient-specific CT scans. And these scans are segmented to create adaptive finite element meshes of bone implant systems, and musculoskeletal simulations provide the patient-specific boundary conditions for their finite element analysis. And some of this work Anne-Christine will present today is actually already published in Clinical Biomechanics. So you can go and check out the paper already if you would like to read the very details of her work. And the presentation will start in a few minutes or so. But just before we start, I will give you a short general introduction and overview of the Anybody modeling system, if there's any of you who are unfamiliar with the software or musculoskeletal modeling and simulations in general. But first of all, I would like to point your attention to the control panel, which appears on the right side of your screen. You are very welcome to submit questions and comments via the question panel during the presentation. And we will try to do our best to address these questions in the very end of the webinar. And in case we do not get to answer all of your questions, then we'll try to do so by email within a reasonable time. So let's begin with having a look at what the Anybody modeling system actually is. Well, the software allows you to do musculoskeletal modeling and simulations. And as input, it takes motion data as kinematics and forces, and it calculates the internal body loads as joint reaction forces, muscle activity, and metabolic energy. And at the moment, Anybody is really used in a wide variety of areas and applications. And just to give you a few examples of this, it could be movement analysis, product design optimization, could be the field of sports optimization, orthopedics and rehabilitation, ergonomics with and without assisted devices, as for example an exoskeleton, and also in the automotive industry. And just to give you an idea of the typical workflow in Anybody, it could look something like this. So you provide the recorded motion data as input, and then you can use the body models which you or others have built. And then you can provide some kind of environment, which could be a special type of equipment, or for example, an exoskeleton. You can then use Anybody to combine these things and solve the muscle recruitment and run the inverse dynamic simulation. And this basically means that we go from motion to calculating the internal body loads and the interaction with the environment in some cases. You can then output the result and use it for post-processing with, for example, some kind of finite element tool. But there's also many users who close this loop completely by doing some kind of design optimization and then run this cycle multiple times. This actually brings me to the end of the introduction, so I'll hand over the presenter role to Anne-Christine instead.
Thanks for the nice introduction and for the opportunity to present our work here at the webcast. So the topic is, again, optimizing fracture healing, realistic boundary conditions. And we start with a short introduction of our share, Applied Mechanics. We are at the Saarland University near the French border, and we are looking into modeling of microstructure continua and the simulation of their mechanical properties. And we have three main research areas like theory, numerics, and experimentation. And we're doing metals, polymers, and biomaterials. And in the biomechanic factor, we are investigating in bone healing, patient monitoring, experimentation, experimental validation, personalized simulation, and also clinical application. And our main current projects in the biomechanic field are the Virtuos project, smart implants, Go Fit Fast, and also an SPP project. And as you can see, we have quite a lot of partners at the moment. So we are quite happy to work together with them and also with their help to set up our current simulations. We start now with a short introduction in the topic. So the overall main topic is the interfragmentary movement. as the key quantity or key parameter for fracture healing. What is the interfragmentary movement? It's like the micromotion between the fracture fragments, the bone fragments in the fracture. And if you have a controlled interfragmentary movement, then you can really stimulate the callus formation. If you have too much movement between these two fracture ends, it can lead to a non-union or delayed healing. And if you have too little movement, we can prevent proper callus development. So it's a unique and individual process, and it's also influenced by different kind of factors like the mechanical loading, type of fixation, the fracture type itself, and also the fracture location. So the main workflow, and we go in every detail on the different parts, but the main workflow is that we like to measure all these red boxes, so the kinematics, the kinetics, anthropometry, and also the EMG data. And then we do like a modeling, so we use anybody for the inverse dynamics to calculate joint forces and muscle forces. And we also use then Abacus for a finite element analysis to look at the bone implant stability and also bone implant connections, and then also for the individual healing. So this is the main part, and we are looking now in every detail in the different methods. And we start with the first method part. So we have the different, we start with the monitoring. As you see, we use Xsens for the kinematics, and we also have like sensor insults for kinetics. Then we use the motion data from the Xsens system to go to anybody and do the inverse dynamics, as I already mentioned, and then go to the boundary conditions. And we look now in every detail for further steps. So we start with Xsens. What is Xsens? It's like a motion capturing system. We at our share, we have two systems. We have the Xsens Link and also the Xsens Avinda. The Link system is, I also can share with the laser pointer, the Xsens Link system is this one. It's like kind of a suit. And the Avinda system is here next to it. It's the shirt with some straps, and but both systems consists out of 17 inertial measurement units and an additional prop. And with the suit, you can measure at 230 Hertz and 100 Hertz with the Avinda system. And as in kinematic output, you get whatever you can imagine, but acceleration, velocity, joint angle, position, orientation. And here in the video, you see quite clearly a patient, and we measure him in his apartment. So for everybody who's not familiar with Xsens, it's location independent, so you don't have to go to a specific room or a specific hospital room or something like this. So you can really measure the patient and his daily activities. And that's really cool. That's why we choose this kind of system. And here you see now 3 examples from different patients. And we also see here in the video that we also have the gloves that fits with the Xsens systems. They are from Manus, and you can really then measure also the wrist and finger movements. Yeah, and it's just example videos of the avatar. So yeah, there's a lot more you can imagine, but yeah, that's just to have a look how this looks like in the avatar. What I already mentioned is that we also have some sensor insults. Yeah, for the kinetic analysis, you see again the same video as before, but now you see the visualization of the ground reaction force from the sensor insults. And also with is here in the image, we also have some kind of load pads for measuring the contact forces between the crutch and the hand, doing the gait with the crutches. And yeah, it's measuring simultaneously to the Xsens system. And also it's a quite nice to have thing that you have kind of a live feedback system, so that the patient can actually look at his weight bearing curves and his ground reaction force curves to see if he's holding the weight bearing that he should hold, or is it too much weight on his fractured leg. So the output would be then ground reaction force, center of pressure, and also then the contact forces from these kind of load pads. And there are different sensor sources available on the market right now. This one is the Novell system, and down here we have the Modicon system. The Novell system are capacitive measurement system, and here we have 16 pressure cells in the sole. So yeah, they're both measured with 100 Hertz. Yeah, and as I mentioned, you can do it simultaneously with the Xsens system. And when we have both of these measurements, we are going to the inverse dynamics. I think it's quite good described in the tutorials from anybody. You use the kinematic output of Xsens via the BBH files, so BioVision hierarchy files, and you import them using the AMR, and then yeah, the kinematic data drive the musculoskeletal model, and the individual models are scaled to the anthropometric data. And you see here an example of a patient in his pre and then his post-operative state. And now when it starts again, you see clearly when he's like lifting the arm that he's in the post-operative scenario, he is really able to lift there on the same height and has a more, can move it better than before. So it's also again quite nice to show the patient at the end what he's now able to do, because it's like, yeah, better to see in this kind of videos. I have some more videos, again, to patients with a wrist movement, this kind of movement where you, yeah, twist your hands up and down, and also again a walking movement. Yeah, that's just two examples to see what we are doing. And yeah, we come to the little bit fun part, is the boundary conditions. So as an example now, it's the tibia. We then calculate the knee joint forces. For example, now the tibia, we calculate the knee joint forces, but I show you later on other examples. And in this case, for example, we measured a patient with crutch. So we measured him doing his partial weight bearing, and then we measure him doing his full weight bearing when he is fully healed. And then we apply these, and the force components are distributed to the nodes. So you see here the nodes of the mesh, and they are also scaled obviously to the body weight. And we are fixing on the distal side. And we are really able to simulate a whole step, not only just the maximum force, but what is actually wished by the medical team, what they want from, what kind of results they want to see, and what they are interested in. So that's how we change the boundary conditions. But for us, it's really important that we use the real gait and the real force data from the individual, and not like an estimated some kind of knee joint force. And here are two examples from two patients. So this one was a humerus patient with his revision, with his initial and current treatment. And as you can see, we use this shoulder joint angle. We measure it with Xsens, and then we use the kinematic data to get then the shoulder joint forces. And we do this again here with the tibia, but then with the knee joint angle. So whatever suits the fracture, we use it as the boundary condition. And the second big part of the methods is the calculation, or not calculation is the wrong word, the creation of the 3D models. We use CT images, so we use DICOM stacks, and then we do a segmentation. We do it with the ScanIP tool or segmentation software, and we also use ScanIP to create these kind of meshes, so these volume meshes. And you see it's always patient specific, from the kind of fracture fixation over the fracture and over the whole situation and position of the bones to each other. And the parameters, the material parameters, are within 6-watt calibration phantom. You see it a little bit here in the DICOM stacks. And yeah, we use this one as to calculate the material properties. And yeah, we do then the FE simulation and then later on the analysis. And yeah, down here are a few publications from us where we describe this whole process in a lot of details. So it's easier to look at this and to really go into every step if you are interested in this. Yeah, now we are going to a little bit to the results. We start with the gait analysis because a lot of the patients we measured are patients who have fractures in the lower extremities, like the femur or the tibia. And yeah, it's really important to understand how the gait cycle, what happens during the gait cycle, and how the people learn to walk again, because at the beginning, obviously, they have to put less weight on their fractured body part, and then they are learning to walk with crutches, and then over the time, over the weeks, they are start to putting more weight on their leg, and yeah, they are then able to walk freely without the crutches. So that's why we are really looking into the different phases of the gait cycle and how they yeah, influence the interfragmentary movement. And that's why we measure in such a detail with the load pads, the sensor insoles, and also the Xsens system to get really every part of this crutch movement. You see here now also a video from somebody walking with crutches. As you see now, we have also visualized the crutch. It's possible in Xsens, but it's just a visualization in the Xsens tool. So as you maybe can see when you look closer, yeah, it's just yeah, for us nice to have. So and also for the patients. And then you see here the diagram from the sensor insoles, because it's here easy to see that the patient has on his right leg, so here with the insole white and the blue, dark blue, he has a weight bearing from around 30 kilograms. And also it's quite good visualized that the load pad left and right, so the measurement of the contact forces between the crutch and the hand is simultaneously with the walk or the step of the right foot, because you have to lean into the crutches, and the left leg is not fractured, so it's a normal movement. And yeah, we tested different weight bearing scenarios, because over the time patients start with normally, but it depends on the area and where you are, and then the hospital, and also on the fracture type. But you start with, for example, a partial weight bearing of 20 kilogram, and then you go up to 50% body weight, and then to full body weight bearing when you are ready. We have a paper at the moment in the peer review process looking at the effects of individual weight bearing scenarios, and we do it in anybody. We implement the text files containing the timestamps from the ground reaction force and the novel load pads, and then we use any input file and any fun interpol to really apply all these ground reaction forces to the foot segment, and have all these data in anybody to then calculate then the specific knee joint forces, but it's also in every detail in the paper, so it's there you can read what I do. So yeah, we estimate the different knee joint forces, and now we look at the simulation to understand what does it mean. We have here a patient with a tibia head fracture, and we for this color visualization, we use the approach from Scheffelbein and Claes to link local strains and stresses to the healing window. They implement or they like created an healing window. And we have here what I mentioned at the beginning with interfragmentary movement. We have parts that have like a perfect healing bone formation, that's the green one, and then we have parts that have the interfragmentary movement is too high, there's too much movement, so this is the yellow and the red, but there are also parts that have too less movement, so this one would be then the blue ones. And what you see here is that when you have a 20 kilogram weight bearing, a 50% body weight and full weight bearing, you see different effects on the fracture. And just to mention, we the segmentation is always with the medical team. So we are talk always with them how the fracture looks like, is everything fine? So it's really a process until we are finished with this kind of 3D models. And you see, because of the fracture treatment, we later on see another patient with another kind of fracture treatment, and as you can see here with a full body weight bearing, there's too much movement, but also with the 50% body weight, and that's more clear if I show the second case, because here in the second case you have another treatment fixation. There are more plates, so it's more stable, so also a 50% body weight has not so much influence than the 20 kilogram weight bearing. When you look at, I just go back, before we already have here a big part. This is in the too much movement area. And also here is again the full body weight bearing. Here shows areas that are in the too much movement window. The material properties here for the fracture gap are from the initial connective tissue. So it's the first part of the healing phase. Yeah, that's why the full weight bearing has so much influence. So if you choose from the dynamic phase of the fracture, if you go later on with another kind of material properties in a further healing phase, then the full weight bearing has another influence, obviously. So, but that's one kind of example what you can play around with, actually. Another big part is then the walking aids itself, so the crutches, how you adjust them. So we tested different scenarios, and here you, for example, you see the walking aids with a correct adjustment. We have here the knee joint angles and the knee joint force, and also out of that we get then the knee joint force, and it's interesting from the anterior posterior and also the proximal distal. But when you look now at the too low adjustment of the crutches, you see a clear difference in the anterior posterior and also proximal distal. So it has an big effect if you just have a false adjustment. And you see this also here in the patient's results with a correct adjustment and then an adjustment too low. And the overall message is that we have an increase in the proportion in the too much movement area from up to 12%. Yeah, but it depends obviously on the treatment situation. When you think back to the treatment with more plates, then it will be again more stable, and yeah, it has not so much effect than on the different weight bearing scenarios. Yeah, that was the first part. It connects also with the walking speed. It's also published in the paper. What was mentioned at the beginning. So if you have different walking speeds, have a different influence, and again on the fracture time, on the interfragmentary movement, and as you see, everything changes from the ground reaction force here to the knee joint angle, and then again to the knee joint force, and also to the elements that are in the different ranges of the healing window. So it's everything, it's like connection between these different parts. Now we are coming to another big part. So as you see, we try to do the realistic boundary conditions, but what you already maybe think of is the muscles. And we are also really interesting to do and create and use the muscles in our models. For example, here we have for the legs and also for, I hope it worked again. Maybe I have to, yes, also here for pronation and supination. We also test this one, what does it with the muscle activation, and again here the videos for different kind of sitting exercises and how they influence then the fracture, yeah, and also the fixation. How do we do it? It's actually, there are two big tutorials and we connect them. The first big tutorial we use is the finite element analysis interfacing. You see the workflow. I took it here out of the tutorial. So it's just that I do what this tutorial says. It's not hard to follow. And then I also use the scaling and personalizing your model. This kind of tutorial, it's also linked down here. Just do, yes, down here. And you see, for example, the red one is the bone from anybody and the blue one is a bone from me or from a patient. And yeah, then we align these to each other and scale them and personalize them. This image is just the first step of a few steps until you are ready. And then you can implement these scalings into anybody and then really create your own finite element mesh. Yeah, and here is the whole workflow, all the differences. We have at the moment often these simplified boundary conditions because we are started with this work on this muscle attachments. There are a few difficulties at the moment, but we have this at the moment, the loading conditions and then also the fixed distal side, or it's again a tibia, but you can do it for the humerus, radius, whatever. And the realistic boundary conditions then would be that we use the force export and we connect it to the volume mesh, as you see here. You see then the different muscle attachments here on the tibia. And then, for example, we tried a two-leg stance just to look at the results and see that we have a fan mesos stress from around 25 megapascal. And then we also start to look how this influences maybe this kind of simple fracture. Yeah, and what is the output of this? That was so the first attempt how to maybe visualize and also use this kind of setup. And we also tried it with the radius, and also the results are quite promising, and I'm quite happy from the results. The fan mesos stress is also, it's in Pascal at the moment because of the dimensions, but it's from the area the same, for example, like the clavicular example of anybody in the tutorials. And yeah, so it's the first attempt to do this. I come later in the outlook, I'll come back to what we are trying at the moment, because obviously we really want to do it with a fracture and also with an implant. And I show you an image later on. Yeah, and last but not least, we are coming to a little bit more results from our new paper. It was published last Friday, so it's really, yeah, it's really new. And yeah, you see here two examples. We have here a radio simulation where we looked at the position from ulna and radius to each other and how the pronation, supination, so the movement of the wrist, influences or what happened there doing this kind of movement. So we measured it with Xsens and then do the muscle forces or the joint forces in anybody and then implement it in Abacus. We also do it for, here's an example for the humerus, which is also published in this paper. It's the main idea of this paper was to publish different digital twins of patients from different use cases. And here we have a case where we have an initial treatment and then here the adaptive plating and how does it influence also the fracture and also the whole fan mesos stress of the implant. Another interesting paper is here from my colleague Roland. where he looked at the different phases of the gait cycle, what I imagined at the start, and how this influences the fracture gap and also the stresses on the implant. And also from him is from 2024, we have this paper where we have the percentage of fracture and the perfect healing window over the stroke of the plate for different fracture gap sizes. So it's interesting that you can play with these kind of simulations with different kind of setups. So you can really look what makes the different, how does the fracture gap size influence the healing, what kind of phase from the gait cycle influence the healing the most, and so on and so on. And the last example, just from the newest papers that we are published, is this one was also already mentioned from the clinical biomechanics paper, where we just have a nice visualization here of the segmentation and then of the simulation results with and without colors. Here you see it's quite nice that we really have these really individual patient-specific boundary, and not only boundary, but this is 3D model that it's really with also the colors and the different fractures. And it's also a result of the close connection between us and the medical team, that we can really work with them together and really create unique results. And look in every detail and the different parts of it. Now I have two different topics at the end that are also a big part from our research. The next topic will be presented by my dear colleague Kerstin Wickert. She's doing the experimental parts at our share, and we are really interested in analyzing also how the plates and the interfragmentary movement behaves, for example, in cadaveric specimens. And that's why she's presenting now a little bit more on the validation part of our work.
So thank you for your introduction. I want to talk a bit more about our human cadaveric specimen experiments. And as a little motivation or introduction, we are interested in why do some fractures heal and other do not heal. So we want to investigate the bone under physiological loading scenarios, and therefore we got two testing devices, one for fracture generation, where we want to investigate what happens during the fracture generation, and we want to define the failure load. And on the other testing scenario, we want to take a closer look at different loading scenarios. So here again, our model with a tibia or a femur fracture, and we apply full weight bearing or partial weight bearing. So for the first testing device for fracture generation, you can see the testing rig on the left side, and we got two different axes. With one, you can see the compression axis, where we got a stepper motor and a screw drive, and we apply a preload to the bone. And the second axis is our torsion axis, where we apply the rotation to our specimen. So we clamp our specimen into this testing device, and then we do the preload first and the rotation at the distal side. So in this case also you can see the tibial bone clamped in this device, and we use for evaluation methods the digital image correlation. So we take pictures or videos of our experiments, and we evaluate later the data with digital image correlation. So it's a pattern recognition, and we calculate then the we calculate then the data. So as I said, the fracture event is caused by the axial preload, and we take this axial preload from the specimen from our antibody measurements, as Ann-Christine said before. And now I got a little video of this fracture generation from the specimen. So you can see here the rotation at the distal side of the tibia, and there we got our spiral fracture on the specimen. So for evaluation, we take a closer look to the fracture formation and the consecutive images, and you can see the 3 images and the spiral fracture. And when we take a closer look, or when we evaluate with the digital image correlation, we can see the maximum displacement at the outer fracture edges in X and Y direction. So as I said before, we use digital image correlation and also measuring sensors. So with these sensors, we are able to measure the upcoming forces and moments during our experiments. And you can see for one specimen here that the force during the experiment rises until 2,700 Newton, and we also got a moment of 90 Newton meters during this fracture formation. We're doing this for a series of distal tibia fractures, and you can see that there's a large scattering from our human cadaveric specimens, and we also tested this with some different soil bone models. So this are composite bones, and they're really close to each other, and the large scattering of the human specimens caused by different diseases, for example, different ages and different material properties from our bones. So the next testing device is our testing device to test the bone implant systems. So when we create our fractures in the first attempt, we then put an implant to it and test it into our second device. And we test daily activities, like here you can see again the Xsens avatar with a walking activity, and we apply these knee joint forces also to our specimen in our testing device. And then it looks like this. With this, we test specimens from lower extremity, for example, the tibia, or here you can see a clamped and treated femur bone. And the second testing device, as I mentioned before, we apply the knee joint forces to our specimen, and we split the knee joint forces in a Z direction, so it's the axial loading, and we got the X and Y components in our horizontal loading. And we are also using, again here, our clamping system, where we clamp our specimen into it, and we're also using our 6 forces sensors to measuring the upcoming forces and also moments. And the goal, why we're doing this, is the experimental validation from our simulations of the bone implant systems. So we got here realistically a simulation of different loading scenarios from our antibody knee joint forces. So with this testing device, we can apply in the Z direction 5 kilonewton, and we can apply 2 kilonewton in X and Y direction. So for evaluation methods, we're using different tools. Again, the digital image correlation, you can see it in the middle. Our camera system with a speckle pattern, you can see it in the next slide. We are also using our sensors and also here the AO fracture monitor to measuring the strains on the implant itself. So for the results, here a picture from the digital image correlation analysis. We first take a look at the implant strain here. So we take a closer look at the change of line length in our axial direction. And you can see on the right side also these typical double hump curves from the Gait cycle. And this pattern, as you saw a few slides before, as an input parameter, yes, you can see it here also very nicely measured from the cameras on our specimen itself. And we are also interested in the interfragmentary movement, as Ann-Christine said before. So we're also doing some analysis in this area, so in the fractured area, and also take a look at the change of line length in this direction. And you can see that there's some differences if you are near to the implant or a bit far away. And to mix all this together, we also run some simulation of this experiment. So we test also full weight bearing and partial weight bearing in our simulation, and also take, next to the implant stability, a closer look to the fracture itself. Also again with this nice little color code, so we can see which areas are in a perfect healing window and which areas have too much movement, or are there some areas with no movement. So with this experimental work, we validate our simulation. And here the last slide is, yes, a nice little final slide where you can see in the red line the results from the digital image correlation, so from our experiment, and with a purple curve there is a finite element simulation results from also the interfragmentary movement, and you can see that we are able to match really good with the simulation the results from our experiment.
Okay, now back to the slide. We already saw a lot in this presentation, but yeah, what we already have now is lower and upper extremities, but a very big or interesting part at the moment in publication and also in research is TMJ surgery and also TMJ simulations. That's why I want to introduce my colleague Michael Roland. We already saw a few publications from him, and that we also are interested now in the TMJ prosthesis manufacturing and in the different simulation types. And yeah, he will present our newest paper. It's published in May 25. So it's yeah, also kind of new.
Hello everybody. I want to show you our latest results on custom-made temporomandibular joint prosthesis. And in this paper we compared two different workflows. One workflow was industrially driven workflow, and the other one was totally on an academic viewpoint. And the main differences are that the academic workflow normally works only on fully segmented image stacks, where the industrial workflows have access to the computer-aided design models of the implants or prosthesis. And on this slide, you can see on the left a threshold-based visualization of the situation of the patient, and in the middle you see the segmented model with the computer-aided design model of the prosthesis, and on the left you see a segmented model of the patient. So here again you see a fully segmented version of the patient with a segmented implant also, and on the right you see how the segmented prosthesis looks like, and compared to the computer-aided design model of the prosthesis, you see that the segmented version has this voxelized structure, and you can see with the image size. And in the simulations, we also want to compare two different cases. Mainly in the planning of the surgery, they added these two screws. We called it in the paper dummy screw, because for medical reasons, they were not able to bring these screws into the patient during the surgery. On this slide, you see the deviation of the segmented implant from the computer-aided design version of the implant. And the deviation is plotted on the computer-aided design model. And of course, there are two areas with a high deviation of more or less 3 millimeters, because these are the two screws which are not included in the segmentation. They are only included in the computer-aided design model. We generated finite element models of all the different models, and you can see here in the middle is our finest mesh. It's the computer-aided design model of the TMJ prosthesis and the temporomandibular joint of the patient. And here on the coarser mesh, we try to compare different contact formulations in the finite element simulation. On this slide, you can see our boundary conditions. We used the standardized musculoskeletal simulation, obviously in anybody, and this is the standard symmetric mandible model published in the early 2000s. And our loading conditions was a molar bite force of 450 Newton placed on the right molar with 450 Newton, and then we compute all the different muscle forces listed on the left side, and we all apply them in our abacus simulation and the industrial workflow. They applied all the muscle forces in an antibody simulation. On this slide, you can see the result of the 450 Newton molar bite force of von Mises stress of the TMJ prosthesis. For reasons of comparison, we normalized the von Mises stress to 1, and 1 means that this is the case where the implant starts to producing failures, and you see that in our case we have 0.2 as value for the von Mises stress, so we are far away from the case that we run into problems. This is the simulation result from the industrial workflow, and now I show you two comparisons with our own workflow, which is based on segmentation. And on this slide, you see the difference between running a simulation without contact formulations and with contact formulations. And you see without contact formulation, we have 1.09 as a maximum for Mises stress, and it reduces to more or less 1 in case of contact formulations. So if you apply contact between implants or prosthesis and bones, you can expect to get a reduction in the stress distribution around the implant or prosthesis. And on the last slide, this is the difference between running the simulation on a segmented model and a model which is driven from computer-aided design. And you see there's a difference from about more or less 10, something like 1.11 and 1.09 is only a few percentage, which are the difference between the two simulation results.
Okay, so we covered the different topics, and I want to close the whole presentation a little bit with the future and outlook, and also a little bit of the take-home message. So our future is that we really want to use more the EMG data. We use therefore DELSIS because you can use it simultaneously with the Xsens system. They are they can be used together, and we really want to look at the initial rehabilitation exercises and how they influence then the fracture gap, and therefore we really want to measure the muscle activities and use this as an additional input. So that is one of the big things we want to achieve. And another one is what I already mentioned, is the muscle attachments. We are really working together with OptiStruct and ANSA to make it possible to use it really with an implant, and to then do with the muscle insertion and insertion points and origin points, that we can put them on the right place where they belong to, and really look the effects then on the fracture gap, and also want to that the muscle attachment workflow is really an automatic workflow, that we do not have to do it by hand. So, and the last slide of our presentation will be then here the take-home message. So at the moment, I don't know if you know, but a lot of the medical team and from our interdisciplinary teams, there's a lot of doubt sometimes regarding the simulations. Is it close enough to the reality? What is the validation? They are actually really like to focus on the best practice, what they are like, what's the normal way to do it, and that simulation is still some kind of a black box for them. And how can we build trust is, I think, the comparison with real data, with the clinical outcome that we like try to give a little bit of feedback, what could be better, and just to have some kind of explanation tool, and also clear explanations what happened in the background, what are the workflows, and also the clear benefits. And so to close everything, the key elements for good simulations, they are, well, simulation has to be appropriate, reliable, valid, and relevant. And we really try to cover, as our group, we try to cover all these points, especially with our cadaveric specimens, to really look into the experimental field and really work close together with the medical team to look at the clinical outcomes, and work together closely with the medical team and the hospitals. So that's the end of the presentation. Thanks for the attention and the opportunity. And do you have any questions?
Thank you very much, and Kerstin and Michael, for presenting your very interesting work. So I think we have time for maybe one or two questions, but just before we go to the Q&A session, I would just like to say a few words about our online resources. So first of all, if you want to know more about Anybody Technology, then you can go and check out our website, anybodytech.com, where you can find different events, special dates, and also all of our previous webcasts. You can also check out our community website called anyscript.org, and this is really for people using Anybody. So here you can find multiple online resources, such as our wiki page. There are several blog posts and also links to our repository sites. It's also here our forum is located, so you can go and ask questions and get help from some fellow Anybody users. Then I would like to mention that Anybody Technology will be present at the Congress of International Society of Biomechanics in Stockholm, Sweden, here in late July. And I know many of you are attending this Congress, so please stop by our booth and let's have a talk and meet each other. And to end the presentation, I would also like to mention that we try to maintain a publication list of all of the papers using Anybody modeling system. And this list has reached more than 1,000 publications, so it's really a great place to go and look and get inspiration on how to use Anybody, but also see which different research groups are using the software and in which different industries and research areas.